Begin this 5 minutes earlier. I need to not do lesson. So the first speaker, the medical speaker, is Henryk Wozniakowski, and here is his title and the beginning of the talk. So Henryk, you're welcome.
Thank you.
We have 35 minutes and 5 minutes for questions.
Okay, good. So thank you very much for organizing this nice workshop. In fact, it's a series of workshops, right? So it's the first one, and that will be how many? Three of them? Okay. So today I would like to talk about exponential tractability for weighted tensor product problems. Now, I'm formally not assuming that you know anything about the subject. So I will try to define everything, and of course many of you are working in this area, so that will be a little repetition for this subset of people, but I think the repetition is the mother of learning, so maybe you can also find something of interest even in this covering study. Okay, so what is tractability? It's relatively a new subject, although, you know, I keep saying it's a new subject, but now it has more or less 25 years. And the idea is that when we study problems with the variables or divariate problems, then we would like to know how complexity depends on D and how complexity depends on the error threshold or the inverse of the error threshold. And before tractability study, the point was only to investigate, in many cases, sharp estimates on 1 over epsilon. And D was kind of a 3-parameter with unknown dependence on D, and of course as long as D is small, then I think it's a fair assumption and tractability for small d does not play any role. But about 25 years ago the situation changed, because we started to talk about the application in finance. And the typical problem in finance was with D equals 360. And 360 was just the total number of months in the 30 years, because the loan is usually done for 30 years. And of course, you see that this 360 is a little arbitrary. Namely, if your bank would like to change the condition of your loan not every month but every 2 weeks, then the result would be 720. A week multiplied by 4, forget that a month is more than 4 weeks, and so on and so forth. So it was clear that D can be enormous. In fact, let me mention that in some financial application, as far as I know, the largest D used in practice for software was in Australia, and I think D was 9,125, whatever. So it's a big number. So the idea, at least theoretically, is to study the dependence also on D. Now, the first work for a number of years was for the so-called algebraic tractability. That means we wanted to relate complexity to D and to 1 over epsilon. So the typical result was to prove or to find the conditions under which you can prove that complexity is not exponential in D and complexity is not exponential in 1 over epsilon. And there are plenty of results along these lines. Now, maybe 7 years ago or 6 years ago, that was a new type of tractability, which is called today at least exponential tractability. Namely, you want to do more or less the same job, but now you want to relate complexity also to the d, but instead of 1 of epsilon, you want to relate to log 1 of the epsilon. So obviously, you know, algebraic tractability is well suited for problems with finite smoothness. And exponential tractability, where you want to have a dependence somehow proportional to log 1 of epsilon, will be good only for C infinity or analytic functions. And the point is that both of them are of interest and both of them are somehow worth to study. And I think the most probably interesting thing is to compare the necessary and sufficient conditions to get algebraic and exponential complexity, and to see how much more we have to assume about the problem to have exponential tractability instead of algebraic complexity. And I will touch this issue. Now, tractability can be studied in many different settings, like worst case setting, average case setting, like probabilistic setting. Just for simplicity, remember I have 35 minutes, I will restrict myself only to the worst case setting, and leaving the other settings not touched, although you can find many papers where different settings are analyzed and studied. Now also, one of the main assumptions which will be used is that we will build algorithms which are using special form of information. And the first class is when we can use arbitrary linear functionals, which is a little of theoretical assumption. And the second class, much more, I think, practical, is when you are using only function values. But again, for the sake of simplicity and limitation of time, I will talk only about arbitrary linear functionals today. And function values will be not touched, but anyhow you can find many papers with a result on function values. Okay, now I'm ready to give you a little more formal definition. What is a multivariate problem? So I have a sequence of operators, and the sequence is indexed by d. So usually d is the number of variables, although, you know, formally on that level it could be anything. And I will restrict these operators to Hilbert spaces for a good reasons. Namely, only for Hilbert spaces there are some more general results. There are some specific results for Banach spaces, but again, for the survey, which I want to give you at least partially, then it's a good assumption about Hilbert spaces. Now, I will be assuming that SD is linear, and also will be assuming that S sub D, the operator, is compact. Compact is a different assumption, namely, without this assumption you can prove many negative results. So compactness is in fact necessary to have positive results. Now, we approximate the value of SD of f by the mappings which may depend on n arbitrary linear functional or function values, as I said before. But in this talk, that will be arbitrary linear functionals. You can choose them using the idea of adaptation, but as we shall see in a second, that will be not really essential. And the worst case setting means that we define the error of its mapping ADN by supping over the unit ball. So SD of f is the exact solution. This is the approximate solution, right? Both of them are in G sub D space. So we take the norm of it, and we are sweeping over the unit ball in the domain space. Now, of course, you know, this quantity can be large, because so far I didn't tell you how to choose this mapping ADN, and if we do a poor job, then of course the worst case error may be arbitrarily large. So that's why immediately I would like to study the best possible choice of ADN, namely the nth minimal error. So I am inifying over all possible algorithms of this form, and this tells me about the intrinsic difficulty of a problem, right? So little n is fixed, so in effect the budget or the cost of its mapping is fixed, and we would like to know how this nth minimal error looks like as a function of d in particular. Okay, and now what is the information complexity? Information complexity is the minimal n, the minimal number of linear functionals which is necessary to compute the nth minimal error at most epsilon. So epsilon stands here, and of course this is a function of two variables, of epsilon and sd of the problem, and the information complexity tells you about the intrinsic difficulty of the problem. Now, it is not the total complexity. I am not telling you how hard it will be to combine this information. I am only telling you how many pieces of linear functionals you need to compute to get an epsilon approximation. Although, as long as you are in the Hilbert space setting, in fact, I am now just quoting the old result, which is well known from 80s or maybe even before, namely that, where is this point? Okay, so we take the operator, which is the adjoint of SD. So W sub D is compact, self-adjoint, non-positive definite, and non-negative definite, and it has a full orthonormal basis, and I'm ordering the eigenvalues. Remember, for simplicity, I defined the problem by normalizing the norm of S sub D, which is the same as assuming that the largest eigenvalue is 1. So we have a sequence of eigenvalues of this operator. By compactness, we know that the lim of them is 0. And it turns out that the information complexity is the first eigenvalue, more precisely lambda dn plus 1, which is less or equal than epsilon squared. And this is the optimal way. What can we do in the Hilbert space setting? Just to take the first inner products, and that's the best possible way. So this algorithm is linear. Adaptation does not help in this sense. So you know, if you want to talk about the cost of computing this, so you need to analyze how hard or how easy it is to compute this sum. Now, you know, in full generality, this lambda d n could be anything properly normalized, and of course, if all of them from the second eigenvalue are 0, then the problem is trivial. So I will assume not to have a trivial problem by assuming that at least I have two positive eigenvalues. Usually, of course, you have infinitely many eigenvalues, and the rate of these eigenvalues will be very important. Okay, so now I think I can return to complexity, to tractability, I'm sorry. So tractability studies the information complexity, and if we compare the information complexity with respect to d and 1 over epsilon, then we have this algebraic complexity, if we compare information complexity to d log 1 over epsilon, we have exponential tractability. And in our book with Erich Nowak, a 3-volume book, 2008, 2010, 2012, at that time really only algebraic complexity has been studied. So you can find many results about algebraic complexity and also many papers written about algebraic complexity. I don't know if Erich would agree with me, but at least 100 papers about algebraic complexity. And after the book was finished, somehow we switched to exponential complexity, and again today we have many but not so many papers as for algebraic complexity where the exponential complexity is studied. Okay, now let me be a little more specific. There are many different notions of tractability. So I will choose one, the most demanding one, and at the end of the talk I will tell you what will happen if we relax this notion a little. So the most demanding notion of tractability is called strong polynomial tractability and abbreviated by SPT. What does it mean? For algebraic tractability, it means that you can bound the information complexity by a polynomial which is independent of d and depends polynomially on 1 over epsilon. Okay, so it's a strong means no dependence on d, and polynomial because you have a polynomial dependence on 1 over epsilon. And of course you would like to have this property, or to prove under which condition it holds, and we would like to have p as small as possible, so this is called the exponent, so the infimum of p for which this holds, right? Because you know, yes, it's a purely theoretical study, but I'm afraid that you can tell me, yes, we have strong polynomial tractability, but my p is 1,000,000. Well, it's a polynomial, right? However, of degree 1,000,000,000, it will take forever to realize this, right? So that's why we would like to know at least, what is the smallest p for which this holds. Now, for exponential tractability, we do basically the same, but we replace, where was it? Yes, we do the same, but we replace 1 over epsilon by log 1 plus 1 over epsilon. And again, no dependence on the upper bound on the information complexity in terms of d, and the polynomial dependence on log 1 over epsilon. This bracket should be higher. Okay, that's the first typo. Probably not the last one. Okay, and again, the infimum of p. Now, in the paper with Peter Kritzer, we decided to find if and only if conditions in terms of eigenvalues to get different notions of tractability. So since we are talking about only one notion about the strong polynomial tractability, it happens that the following is true, that for the algebraic complexity, for algebraic tractability, this SPT holds if and only if the sum of normalized eigenvalues raised to some power tau is finite for all d. And the exponent of SPT tractability is 2 times tau, where tau is from above, right? So infinite over tau and times 2 will give you the exponent. Now, if we switch to the exponential tractability, then the condition is different. Namely, we need to assume, because it's if and only if, that the sum of the normalized eigenvalues raised to the power j to minus tau is finite for all d. And again, the exponent is 1 over tau, where tau is the smallest possible number satisfying this bound. So that means we know what do we have to assume in terms of eigenvalues to get strong polynomial tractability for the algebraic and for exponential case. Okay, now let me specify this result for some specific problems. So I will take unweighted first tensor product problems. Okay, tensor product is our, I think, one of the beautiful source of examples of multivariate problems. And here you have a univariate problem. You have d tensor copies of this univariate problem, and the same you are doing with the spaces. And this univariate problem is linear and compact, and you have eigenvalues for the univariate problem, and you are normalizing everything by assuming that the largest eigenvalue is 1, and to omit the trivial problems, we are assuming that the second largest eigenvalue is positive. Now it's easy to check that for the d-variate problem, the eigenvalues are given by the product. That's why, tensor product problems are nice to analyze. And we take the product of the univariate problems, and that's what we have. Now, since we assume that lambda sub 2 is greater than 0, then for the d-variate problem we have at least 2 to the d positive eigenvalues. So we have exponentially many positive eigenvalues. So there is a room to play. Now, again, the first negative result, we take the unweighted tensor product problems, and it turns out that the strong polynomial tractability never holds. Doesn't matter if you take the algebraic case or the exponential case, the SPT does not hold. The problem is too difficult to allow to have strong polynomial tractability. Although, just to make a little this negative result a little sweeter, I said that if you weaken notions of tractability, you may find the positive result. Now, with our machinery, nowadays it's almost trivial to prove it, right? Because what happened? Okay. Namely, it's enough, of course, to show the less demanding notion, namely algebraic strong polynomial tractability. And in this case, we know that this holds if and only if this series is uniformly bounded in D. But it is 1 plus lambda 2 to the tau to the D. Now you see why I need to assume that lambda 2 is positive, right? Because if lambda 2 is 0, then everything would be okay. But for lambda 2 positive, there is an exponential function of D, so that's why there is no way to get the strong polynomial tractability. Okay, now if you see this negative result, then of course it's a kind of a tautology. You may say, well, because my problem is too general, so I want to find another restriction of my problem to kill this negative result. And that's a natural way to go to the weighted tensor product problems. And let me now spend a minute or two for this slide. The idea of the weights is very important in the subject. So, so far, you know, we started with unweighted tensor product problem with, again, the eigenvalues for the univariate case, and now we introduce gammas. So we have a sequence of gammas, again for simplicity, assuming that the largest of them are at most 1, that they are ordered, they can go but not necessarily to 0, and the weights are used to change the norms in the spaces. So now instead of f sub 1, I'm using the space f1 gamma k, and here's a new norm. So you see, if I take gamma k equals 1, that will be the norm as before. But now gamma k is not necessarily 1. In fact, the interesting case is when gamma sub k is small. So if gamma sub k is small, and if we are still in the unit ball, then we control that this must be very small. And it goes up to the limit. If gamma sub k is 0, agree, then the sum must be 0. So that means the smaller gamma, the smaller the space. Of course, I don't want to trivialize the problem, but my idea would be to ask what are the necessary and sufficient conditions on gammas in particular to get strong polynomial tractability, or whatever tractability I have in mind. So that's the role of weighted spaces, and in fact, you know, through the gamma sub k, we control the dependence of the kth component. Now, it makes, I think, a kind of a sense that if you are talking about a problem with many, many variables, let's say 360 for this finance problem, that I think it's easy to believe that not all variables are equally important. So that means some of them are more important than the others one. So all people are equal, but some of them are more equal, right? So this is the idea. And the idea is to quantify what do we have to assume about some decay of gamma sub k to get a positive result. Okay, and now weighted tensor product. So for the weighted tensor product, you know, we have the same operators because they are now defined on the, in particular, subclasses. And the only thing which we did is we changed the eigenvalues, namely if the largest eigenvalue is still 1 as it used to be, but the rest of them are multiplied by gamma sub k. So that means if we take the unweighted case, then we have a situation as before. But of course the whole thing is not to assume that gamma sub k is 1, and then you have an extra decay of the second to the third and so on eigenvalues. And back to strong polynomial tractability. So now we want to find if and only if conditions on lambdas and on gammas to get this property. So for algebraic case, again, algebraic case means I'm repeating this definition that I have a bound on the information complexity which is a polynomial in 1 over epsilon. So this holds if and only if the sum of the gammas is summable with some exponent tau, and the sum of lambda sub j is summable with some maybe different exponent tau. And here I take the smallest possible tau for both cases. And this property, being strong polynomial tractability for the algebraic case, holds if both of them are less than infinity, and then the exponent is equal to 2 times max of these two numbers. In fact, you know, this theorem, at least the first occurrence of this theorem, was proven by Greg Wozniakowski and myself already in 1999, but the most general case with all possible generalization, which I'm not covering here, it's covered in theorem 5.7 in volume first of our book with Erich Nowak. Okay, so that's algebraic complexity. How about the exponential tractability? That's the recent work with Fritz Pilitzhammer and Peter Kritzer. So again, this is a repetition. Now we would like to have a bound which is a polynomial in log 1 over epsilon. And you know, this is just the repetition that both of them must be tending to 0, and the following lim sup must be finite. What is d of epsilon? What is j of epsilon? So d of epsilon is the smallest k for which gamma sub k is greater than epsilon squared. J of epsilon is a maximum k for lambda k greater than epsilon squared. And the exponent is this property. Now I prepare some example, but I'm afraid that I may not have time to cover this example, so let me go to the further results for exponential tractability. Again, of course, they also exist for the algebraic complexity, but I would like to concentrate on the new work with Fritz and Peter. So, and here you will see how this notion of tractability can be relaxed. So now the first, I think, natural relaxation is polynomial tractability. So by polynomial tractability, you mean that you would like to have a bound on the information complexity which is a polynomial in log 1 of epsilon, but also a polynomial in D. So before, a strong polynomial tractability corresponded to Q equals 0. Now Q can be anything. And it turns out that unfortunately this relaxation gives us nothing, namely this polynomial tractability for exponential tractability holds exactly when we have SPT. Of course, you know, one implication is trivial. I mean, strong polynomial tractability implies PT. The only way to prove is that polynomial tractability implies strong polynomial tractability. Then we go to the so-called QPT. QPT stands for quasi-polynomial tractability. That was a notion defined a couple of years ago by Michael Gnevov and myself. Michael, where are you? Oh yeah, what was the year of our paper? 2008? 11. Oh, so late. Okay, in any case, so now look what we are doing. Namely, we relax that the exponent can slowly increase with d through logarithm. Okay, t times 1 plus log d. So that's why QPT is a weaker notion than polynomial tractability, right? Because polynomial tractability, it will be a constant. And it turns out that, yes, we have a different result, namely exponential tractability and QPT holds if the following condition is true. So again, you know, this limit must be finite, and you may remember that for SPT we didn't have this log, so slightly related, but a little less is required. And the infimum is just this limit. And now let me go to the last notions. That's the notion which was defined by Markus Weimar and Paweł Siedlecki. Markus, what was the year? 2013?
Maybe.
More or less. Plus or minus 10? No, plus 1. Okay, so you take two parameters, S and T, positive, and you would like to check that our information complexity is not exponential in d to the power t and is not exponential in s power of log 1 over epsilon. Of course, Markus and Paweł, they did it for algebraic case, so it was 1 over epsilon, but of course it's the same idea that you put log. And the following results are true, namely if both parameters are 1, so that means if S and T is 1, it's a kind of the most common case studied before, then this holds if the sequence of the weights goes to 0 and the sequence of eigenvalues goes sufficiently, I mean 1 over lambda sub j goes sufficiently fast to 0. It must go faster than polynomial, right? And this is if and only if. Now, if you assume that still S is 1, but T is less than 1, then of course you are asking for more, so you need to assume more about gammas. You have the same condition on lambdas, but you have a different condition on gammas. It's more or less the same condition on gammas. So both of them must go to 0 quicker than polynomially. And finally, the result if t is greater than 1, that's a kind of a positive result. In this case, you do not have to assume anything about gammas, so you can switch back to the unweighted case, so you can take all gamma sub k equals 1, but you must assume the same condition on lambdas. Now, for the first slide, I told you that the work with Fritz Pillishammer and Peter Kritzer is still work in progress, and the point to be in progress means to generalize this theorem for different s's and t. I think we are done with s greater than 1. I didn't put these conditions because, you know, it's a kind of boring to see a variation of different conditions, but we have troubles to prove if s is less than 1. And so the work will be done if all the cases are treated, and also, you know, because we know how it behaves for algebraic complexity, then the comparison to see how much more you have to assume in terms of gammas, in terms of lambdas, to get a more demanding notion of tractability. Okay, guys, I have now good news for you. That's all. Many thanks for your attention.
Thank you very much, Henryk. Now, questions, comments? Yep.
Maybe one short question concerning the last result. You said the gammas are arbitrary, but some slides before you said they have to be universally bounded.
I mean, arbitrary in this sense. I mean,
what happens if you don't assume?
I mean, if I assume that they are bounded, but not necessarily by 1, the result is the same. But if they go to infinity, the result is different, or maybe different, depending on lambda. I mean, not if and only if. But we know that the result will be different for some gammas.
Other questions? If no more
Yeah,
problems.
you know, if you,
Okay, go ahead.
Maybe you can mention some open problems in this topic.
well, you see, I already mentioned the open problem s less than 1, but of course it's a kind of a local problem for this project. Now, in terms of challenges, I think the idea is to study tractability, that means dependence on D, of multivariate problems. Not necessarily of this form like tensor products or weighted tensor product. I think that will be a very interesting talks, at least by Thomas, but maybe also by Winfried, about the Sobolev spaces, and they are not tensor products, so it's a different spaces. They require different proof techniques to get tractability and so on and so forth. So it means that was just only the instance of a problem for which you can illustrate, but the idea would be to, as long as D is large, also to study how complexity depends on B. And that's like a general question. And of course, you may have a negative result or the curse of dimensionality in many cases, and then you are looking for what are the minimal shrinkage of a space not to have the curse of dimensionality, and so on and so forth.
Okay. Other questions? If no more questions, let's thank the
Thank you.